complex Lewis structures. In this section, we'll give a more complete coverage of resonance as well as bond order. Resonance is when a single Lewis structure is an incomplete description of the bonding. In these cases, we say the molecule is a resonance hybrid of the multiple resonance structures. Bond order refers to whether a bond is single with one shared pair of electrons, double with two shared pairs, or triple with three shared pairs, or somewhere in between. First, resonance structures, when a single Lewis structure does not fully represent the molecule. Resonance structures have identical skeletons. That means they have the same central and peripheral atoms, bonded to each other in the same order. A quick word about bonds. Sigma bonds have their electron density in the bond axis. Sigma bonds are formed from end-on overlap of orbitals. For instance, we could have an s orbital overlapping with the p orbital. This forms a sigma sp orbital. The bond axis is a line connecting the two nuclei. Sigma bonds are also the first bond formed between two atoms. Pi bonds, on the other hand, have their electron density outside of the bond axis. This is caused by side-on overlap of parallel p orbitals. There's a set of p orbitals parallel to each other on two different atoms. When you move them together, you get this pi pp bond. It has two lobes of electron density. One here above the bond axis, and the other down here below the bond axis. And you can see that neither lobe of electron density is in the bond axis, they're both outside. Finally, pi bonds are never the first bond formed, but rather the second bond and/or the third bond. Thus, when we look at a Lewis structure, we can determine some things about the bonding composition. So, bond order can be single, double, or triple. When you see a single bond in a Lewis structure, its picture is just one dash, that's one pair of electrons. Since we know that the first bond formed between any two atoms will always be sigma, a single bond is always one sigma bond. Here's a picture of a double bond. The two dashes represent two shared pairs of electrons. Now, one of those bonds in the double bond is sigma, because the first bond formed is always sigma, but the other one is pi. So the composition of a double bond is always 1 sigma plus 1 pi. Here's a picture of a triple bond between atoms A and X. The three dashes represent three shared electron pairs. The first bond formed between them is sigma, so there's one sigma bond in there. The second and third bonds are pi, so there are two pi bonds. Hence, when you draw the skeleton of a molecule, the central atom has a single bond to each peripheral atom. All of those bonds are sigma bonds. And that means that resonance structures differ only in the placement of their pi bonds and their lone pairs. Now we're ready to draw some resonance structures. Recall the rules for drawing Lewis structures. Recall that we first have to count the electrons, then draw the skeleton, recount, fill in the remaining lone pairs, check everything for the octet rule. Let's look at the molecule SO2. Sulfur and oxygen are both in group 16, so they have 6 valence electrons per atom. There's 1 sulfur and 2 oxygens, so 6 plus 12, 18 electrons total. In the skeleton, we're going to put the sulfur in the center. Now, the reason we do this, normally we put the atom with the most unpaired electrons in its Lewis symbol in the center. But you can see both sulfur and oxygen have 2 unpaired electrons. So, to break the tie, we go to electronegativity. Sulfur is less electronegative than oxygen, so sulfur goes in the center. Again, that thing about electronegativity is a tiebreaker. So back to our skeleton. We had 18 electrons and we formed 2 bonds. So we subtract 4 electrons from our 18. That gives us 14 more electrons to put in. And we start out by putting them in as peripheral lone pairs. 2, 4, 6, 8, 10, 12, 14. Now we check all our atoms for the octet rule. The oxygens both have 3 lone pairs and a sigma bond, so 8 electrons each. The sulfur, on the other hand, has 2 sigma bonds and a lone pair. That's 3 pairs, or 6 electrons. Sulfur is not happy. What do we have to do? We have to change one of the lone pairs on oxygen into a pi bond between sulfur and one of the oxygen atoms. So which lone pair do we use? Well, we have the option of 2 different oxygen atoms. We could take this lone pair and change it into a pi bond, and that leads to this structure. Now, the oxygen over here has 2 lone pairs and 2 bonds. It still has 8 electrons. The oxygen on the right hasn't changed. But now sulfur has 3 bonds in a lone pair. That's 4 electron pairs, or 8 electrons. But we could just as easily use a lone pair from over here. That leads to this Lewis structure on the right. And you can see every atom has 8 electrons. So step 4 leaves us with these 2 resonance structures. We connect resonance structures with a double-headed arrow, like that. Now, a single bond is long. It's got a longer bond distance. A double bond, on the other hand, is short. If the molecule were either one of these 2 structures, we would see one of the SO bonds, the single bond, being a long bond, and the other bond being short. In reality, that's not what we see. When we look at the actual structure of the molecule, first we see that both bonds have an equal length, but also both bonds are longer than a double bond. Not only are the bonds longer than a double bond, they're shorter than a single bond. What does this lead us to conclude? Each bond must be more than a single bond, that is, more than one shared pair of electrons, but less than a double. The bonding in the resonance hybrid is the average of the 2 resonance structures. So each bond is actually 1 sigma plus 1/2 of a pi bond. And the bond order, or BO, for each bond in the molecule is 1.5 or 1.5. How do you calculate bond order? We calculate our bond order by summing up the total number of bonds in the molecule and dividing it by the number of atom pairs that are bonded to each other. From the resonance structure on the right above, we can see that there is one bond plus two bonds. That's three bonds. That's the numerator of our equation. So, in our fraction for bond order, 3 goes in the numerator. On the bottom is the number of bonding atom pairs. The sulfur and the oxygen on the left, that's one pair of atoms that are bonded to each other. The sulfur and the oxygen on the right is another pair. 1 plus 1 is 2. Thus, the bond order for each SO bond in sulfur dioxide is 1.5. A greater bond than a single bond, which has a bond order of 1, but a lesser bond than a double bond, which has a bond order of 2. And you can think of it as the pair of electrons that comprise the pi bond are delocalized. Here's an exercise for you to try. Draw all the resonance structures of sulfur trioxide. Pause the video while you work. Unpause it when you're done to compare your answer with mine.